often start with force and motion because it then feeds into different topics. So we can talk about energy using forces. We can talk about gravitational fields. We can talk about magnetism and electricity. We can use a lot of these concepts in forces. With forces, a force really is push or pull, and they often have the unit of newtons. So forces, we state them in units of newtons. This is really important skill in physics, actually. It's to always write your units in what we call the SI units. This is almost like your physics language, really. This is how we use measurements. Physics it's a very communicative subject. So I could often speak to researchers from different countries, be it Japan or other countries like that, France. So we need a language or a means to communicate. In SI units is often that way. So when I say SI, it's often refers to things like meters. So looking at length scale. So you can use length for meters. We can measure current in amps. We can also measure force in newtons. So it's just the construct of how we write our units and how we communicate like equations and stuff like that. So current and newton force. These quantities, they can be grouped up into two different groups, be it scalar quantities, which have magnitude and no direction, and vector quantities, which, as you know, probably they have both a magnitude and a direction. So a classic example for a vector is something like a force. We know forces, we draw them with arrows, for example. So in a free body force diagram of a ball, we know that the weight of that ball is acting downwards, and then some sort of reaction force, be it a resistance or some friction, acts upwards. See the language I'm using here, downwards, upwards. If you're using that language, it's solely tied to a vector way of thinking. So it's a vector essentially. So if we have a look at these quantities here, we've got things like mass, distance, acceleration. These can be really tied down to either a vector or scalar. So things like mass, that is going to be a scalar quantity. It's just a measure of matter in an object. Distance is a scalar quantity. And often these things have like pairs. So mass is the scalar, but you can also think of mass as weight, can't you? Except that weight is sort of the vector equivalent to mass. So weight is a vector because it acts downwards, like here. And it's also worth noting that weight is equal to mass times the gravitational field strength. So weight, that has a direction, so it's a vector. Then distance, acceleration. This is interesting. So acceleration is also a vector. How do we know this? Well, you can either you can be in a state of acceleration or deceleration, and to dictate how things accelerate, it could be accelerating upwards, it could be accelerating to the right, downwards. So this has a direction, and so therefore is a vector. I think a good way to visualize this is to look at Newton's second law as well. So F equals ma. This is a common thing that physicists do, actually. So it's worth noting that this, I think, is the most formal way of writing Newton's second law. And you can see I've noted these underlined F and I've underlined A. This is to denote the fact that A is a vector and M is a scalar. So this is nice practice, really. If you want to denote if something is a vector or not, you can just underline it and state that it's a vector. So, for example, like if I want to go from A to B, write it in this notation. But this is basically equivalent to writing, say, AB underline like that. There's different practices. I find it's quite helpful to underline those things. So acceleration is a vector. Speed is a scalar. Speed, we don't necessarily designate its direction. So when you look at a speedometer or whatever, that doesn't care about a direction. That just looks at what is your total speed right now. It doesn't matter if it's sideways or horizontal, vertical. It's just what is the pure speed that you're going at the time. It doesn't care about direction. But velocity certainly does. Velocity is the vector equivalent. So we also have energy and time. Energy is also a scalar quantity. Energy doesn't have direction, nor does time. And the same can be said about power as well. And if you look at these quantities here, so we have energy, time, and power. You can relate all of these together. The energy formula. So power is equal to energy over time. And you can see how all of these quantities here are scalars, so it is consistent. So if you said, oh, power is a vector, well, that has to imply that either energy or time is going to be a vector, and that can't be true. You have to sort of conserve left-hand side, right-hand side, is a vector or scalar or not. And then you can see with Newton's law, then that case is actually true. So in the left-hand side, everything's a vector. And on the right hand side, everything's a vector because you have m times a, so another vector, be it a prime or something. You can see that that vector scalar notation is served. So that's also, I think, worth noting. You can combine all of these scalar quantities together to give you an equation. W, in this case, is weight, essentially. But I can write Newton's second law and as F equals ma. So if my force is purely weight, then you can see these equations sort of line up, don't they? So weight is the equivalent of my force, the masses are the same, and you can deduce that the acceleration is the constant g in this case. So that's all it means. It's just an expression of weight, but weight is equal to the mass times gravitational force strength. We'll have a look at this in a bit more detail later. Done power. All that's left, we've got force and displacement. So distance and displacement, that's another pair that we have between vector and scalars, distance and displacement, and also force. We'll just put here, we know force, that has direction like displacement. It's going to be vector. A nice example I like to think of displacement is consider when you were born, for example. So I was born in Wigan. My displacement so far is about a mile or two. So for all my 19 years of living, I've moved about 2 miles, apparently, according to displacement. Whereas if you consider distance is the amount of, I don't really estimate my distance, but it's going to be substantially larger than 2 miles. So that's just a nice example. Just think of your position now relative to where you were born. That's your displacement. Whereas your distance is all the that you travelled during your time living on Earth. I suppose that's a nice little comparison between these two. Another thing worth noting is how we resolve vectors. So if one vector is at right angles to another, then we can use Pythagoras' theorem to work out that resultant vector. So all this is saying is if I have a vector A and a vector B, like this, then I can work out what the net result of that vector is by resolving these two forces. And you can see, because it's at right angles, I can just resolve it and join the two like that. And that's Pythagoras' theorem, isn't it? So we know that a squared plus b squared is c squared. So to work out the magnitude of this resultant vector, we can just take the square root of both sides to give us the resultant vector magnitude.